Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to explore the largest marine prey. I spoke about the largest predators 2 videos ago, and now I will speak about marine prey. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. Antarctic krill, Euphausia superba, is a tiny crustacean reaching up to 6 centimeters in length and weighing up to 2 grams. On its own, it accounts for the most astonishing calculation of any known marine prey species. In the Southern Ocean, this single species adds up to an estimated biomass of around 379 million tons, more than the entire human population of the planet. Antarctic krill biomass has been estimated at 0.05 gigatons of carbon, a value similar to the total biomass of humans at 0.06 gigatons of carbon. Each individual krill weighs less than a coin. Together, they outweigh the entire human species. It's one of the largest individual living resources known on Earth. Picture weighing every single human being alive today separately. All 8 billion of us combined on one giant scale. Now picture another scale on the opposite side, holding nothing but tiny crustaceans about the size of a pinky finger, caught in the freezing waters near Antarctica. Surprisingly, that second scale would tip heavier. This isn't rhetorical exaggeration. It's a verifiable biological calculation backed by decades of oceanographic research. An animal small enough to fit in the palm of your hand adds up, at the population level, to a mass greater than the sum of all humanity. Billions of people, each weighing dozens of kilograms, still outweighed by organisms that are practically microscopic by comparison. Crustacean is the technical term for this group of invertebrates, which also includes shrimp, crabs, and lobsters. Krill belongs specifically to the order Euphausiaceae, characterized by transparent or translucent bodies, multiple swimming legs, and protruding compound eyes. Unlike crabs that crawl along the ocean floor, krill swim actively through the water column, propelled by thoracic appendages that beat rhythmically. This constant mobility enables daily vertical migrations, rising near the surface at night to feed, then sinking to greater depths during the day to avoid predators that hunt by sight. Biomass, the central term in this comparison, refers to the total weight of living organisms in a given area or population, usually measured in tons. It's different from a simple population count. What matters isn't how many individuals exist, but how much they weigh collectively. A small population of large organisms can match, in biomass, a massive population of tiny organisms. In the case of Antarctic krill, the math works through sheer multiplication. Trillions of individuals, each weighing just grams, add up to hundreds of millions of tons. Scientists calculate this biomass through acoustic sampling, trawl nets, and statistical models applied across vast ocean areas. Carbon also serves as an alternative unit of biological measurement, especially useful for comparing species that are very different in body composition. A gigaton equals 1 billion metric tons. When researchers convert krill biomass and human biomass into this carbon-based metric, the numbers come strikingly close, both hovering around 5 to 6 hundredths of a gigaton. That numerical convergence, while something of a coincidence between such evolutionarily distinct species, illustrates an impressive scale. Organisms under 2 centimeters long, multiplied across astronomical populations, match the accumulated weight of an entire dominant land species, one capable of building cities and traveling to space. The geographic distribution of Antarctic krill is concentrated mainly in the cold waters surrounding the icy continent, a especially in the Scotia Sea and regions adjacent to the Antarctic Peninsula. Low temperatures, specific ocean currents, and an abundant supply of phytoplankton, microscopic algae that serve as their primary food source, create ideal conditions for massive reproduction. Unlike species spread widely across global oceans, Antarctic krill stays relatively confined to this polar region, concentrating its colossal biomass within a specific geographic area, which makes population densities even more extraordinary when measured per square kilometer. The ecological importance of this biomass goes well beyond impressive numbers on their own. Krill functions as a fundamental link connecting microscopic primary producers, phytoplankton that capture solar energy through photosynthesis, to massive predators at the top of the food chain. Whales, seals, penguins, and a variety of seabirds depend directly or indirectly on this crustacean for survival. Without this colossal abundance, the entire Antarctic ecosystem would collapse structurally. Few organisms on their own sustain enough biomass to feed so many predator species simultaneously across such a vast geographic scale. Each individual krill lives for about 6 years under favorable conditions, a relatively long lifespan for such a small invertebrate. During that time, it molts repeatedly, shedding its exoskeleton as it grows. Reproduction happens seasonally, with females releasing thousands of eggs that sink to considerable depths before hatching. The larvae then gradually rise back up through the water column, developing through successive stages until reaching adult form. This efficient reproductive cycle, combined with a lack of significant predation during the early stages, allows populations to stay large enough to sustain a biomass comparable to all of humanity. Researchers constantly monitor fluctuations in this biomass, concerned about the potential impacts of ocean warming and growing commercial fishing. Krill is harvested industrially to produce omega-3 rich oil, meal for aquaculture, and human dietary supplements. Although current catches represent a small fraction of the total estimated biomass, climate change altering ocean temperatures and currents could significantly affect this species' reproductive capacity. Understanding the mechanisms behind this extraordinary abundance is essential for predicting the consequences of environmental changes on the entire Antarctic ecosystem, which depends fundamentally on this tiny but collectively colossal prey species. Understanding this equivalence between the biomass of a tiny crustacean and that of the entire human species sets the stage for the next question. How do such small organisms manage to form aggregations dense enough to be literally visible from outer space? A phenomenon that reveals unique behavioral mechanisms governing the collective life of these seemingly simple yet remarkably coordinated animals. This prey species scale doesn't come from individual size. It comes from extreme concentration. Antarctic krill live in large schools, called swarms, sometimes reaching densities of 10,000 to 30,000 animals per cubic meter. These super swarms are so massive they can be seen from space. A single cubic meter of water, roughly the size of a phone booth, can hold 30,000 individuals swimming in sync, forming a living cloud visible by satellite, stretching across kilometers of Antarctic Ocean. No other marine prey species forms aggregations of this density on a comparable scale. A cubic meter is an easily visualized unit of volume. A cube measuring 1 meter on each side, roughly equivalent to the inside of an old phone booth or a large home freezer. Imagining 30,000 small animals packed into such a tight space defies common intuition about biological density. Each krill, though small on its own, takes up three-dimensional space. Multiply that by 30,000 within such a confined volume, and there's practically no free water left between bodies, creating an almost solid mass of living organisms moving in coordination through the polar ocean. Swarm, the technical term applied to these aggregations, is different from simple random grouping. It's organized collective behavior, where thousands or millions of individuals sync their movements through visual and likely chemical signals as well. Each krill maintains a relatively constant distance from nearby neighbors, adjusting speed and direction in response to changes in the surrounding group. This behavior, while it doesn't involve conscious communication comparable to humans, results in complex emergent patterns. The entire mass moving as a unified entity, suddenly changing shape and direction to dodge predators or take advantage of favorable currents. The spatial visibility of these swarms is an extraordinary phenomenon rarely associated with such tiny individual organisms. Satellites orbiting hundreds of kilometers above Earth's surface can detect changes in ocean color caused by massive concentrations of krill, whose reddish or orange-tinted bodies alter the tone of the surface water. Captured images show irregular patches stretching for kilometers, contrasting visibly with the deep blue surrounding them. These superswarms, occasionally covering areas comparable to entire cities, demonstrate a truly impressive scale achieved through extreme aggregation of individually tiny organisms. The biological mechanisms behind this dense formation involve multiple combined factors. Concentrated food availability, patches rich in phytoplankton, draws krill to specific areas, creating an initial concentration. Protection from predators also favors grouping. Being surrounded by thousands of similar individuals lowers each individual's odds of being caught, a phenomenon known as risk dilution. Additionally, ocean currents and temperature patterns can passively concentrate planktonic organisms, including krill, in certain regions through physical processes independent of the animal's own active behavior. The swimming synchrony observed within these swarms superficially resembles behavior seen in fish schools or bird flocks, although the underlying sensory mechanisms differ considerably. Krill have sensory organs capable of detecting vibrations in the water, possibly allowing each individual to track the movements of nearby neighbors without needing direct visual contact, especially relevant at depths where light is scarce or absent. This sensory capability, distributed across thousands of individuals simultaneously, produces emergent coordination without any central organism controlling collective movement. Predators face a peculiar challenge when dealing with these massive concentrations. Whales, especially species like the blue whale and the humpback, have developed specific feeding strategies to efficiently exploit these dense swarms. Diving through the concentrated mass of krill, these whales gulp down enormous volumes of water containing thousands of prey at once, later filtering it through specialized structures called baleen plates. Without this extreme density, efficient capture would be impossible. Whales would burn a disproportionate amount of energy hunting individually scattered prey across the vast ocean. Seasonal variation significantly affects the formation and persistence of these superswarms. During the Antarctic summer months, when extended sunlight drives explosive phytoplankton growth, conditions become especially favorable for massive krill aggregation. Polar winter, marked by prolonged darkness and extensive sea ice cover, shifts behavioral patterns, with krill possibly feeding on algae found on the underside of the ice, sustaining themselves during a period of relative food scarcity in the open water column. Researchers use sophisticated acoustic technology to map and quantify these swarms without needing extensive physical sampling. Sonar emits sound pulses that reflect differently depending on the density of organisms present in the water, allowing scientists to build three-dimensional maps showing krill distribution and concentration across vast ocean areas. Research vessels systematically navigate predetermined routes, continuously collecting data that's later processed computationally, generating reliable estimates of the size, shape, and population density of these extraordinary aggregations. Understanding how these extreme densities form only reveals part of the full ecological story. What remains is examining how this concentrated abundance is simultaneously consumed at an intense pace by a variety of predators, maintaining a dynamic balance through constant reproduction that prevents population collapse despite the massive predatory pressure continuously exerted on this species, which is fundamental to the entire surrounding Antarctic ecosystem. This prey species doesn't just exist in colossal quantities. It's consumed at an equally colossal pace, without collapsing. More than half of this biomass is eaten by whales, seals, penguins, seabirds, squid, and fish every year. Of that total, more than half is eaten by whales, seals, penguins, squid, and fish annually, and it gets replenished through reproduction and the krill population's subsequent growth. All predators combined consume between 152 and 313 million tons of krill every year. Seals alone consume between 63 and 130 million tons, whales between 34 and 43 million, birds between 15 and 20 million, squid between 30 and 100 million, and fish between 10 and 20 million. It's the prey species that, on its own, sustains practically the entire food chain of an entire ecosystem. Considering that more than half of an entire population disappears every year, devoured by a variety of predators, would intuitively suggest an imminent collapse for just about any species. Yet Antarctic krill defies that expectation through an extraordinary reproductive capacity, offsetting massive losses through constant population renewal. This dynamic balance, maintained for thousands of years, shows how functioning ecosystems can sustain seemingly unsustainable levels of predation when the base species has a reproductive strategy robust enough to compensate for proportionally enormous losses continuously inflicted by multiple specialized predators. Seals are the biggest individual consumers of this biomass, devouring between 63 and 130 million tons annually, a considerable range depending on species, population, and the specific environmental conditions of each season. The crab-eater seal, despite its misleading name, feeds almost exclusively on krill, with specialized teeth featuring multiple cusps that work like a sieve, letting it filter small crustaceans directly from the water while expelling the excess liquid. This specific anatomical adaptation shows coevolution directed specifically toward efficiently exploiting this abundant and predictable food source. Whales consume between 34 and 43 million tons, a smaller amount compared to seals, but still impressive given the individual body size of these species. The blue whale, the largest animal known to have ever existed according to current scientific understanding, can consume the equivalent of millions of individual krill per day during the intensive feeding season. The lunge feeding technique, a quick dive followed by a massive opening of the mouth, swallowing huge volumes of water and prey at once, allows it to process extraordinary amounts of biomass in relatively short periods, making up through efficiency what it lacks in sheer population numbers. Seabirds, although consuming a proportionally smaller amount, between 15 and 20 million tons, play a significant ecological role due to the diversity of species involved. Penguins, albatrosses, petrels, and other birds adapted to polar environments rely heavily on krill during breeding periods, when energy demands rise substantially to feed growing chicks. Active diving, especially characteristic of penguins, allows direct capture of krill at depths that birds hunting only from surface dives can't reach. Squid make up a predator group that's often underestimated in this equation, consuming between 30 and 100 million tons, a wide range reflecting the inherent difficulty of studying cephalopod populations that live at considerable depths and are rarely observed directly. These agile predators, equipped with specialized tentacles and exceptional swimming ability, efficiently exploit krill concentrations both in surface waters during nighttime migrations and at greater depths during daylight hours, when krill sink to avoid visual predators. Various fish round out the predatory picture, consuming between 10 and 20 million tons annually. Species specifically adapted to cold Antarctic waters have developed varied feeding strategies to exploit this abundant protein source. Some fish filter directly from the water column. Others actively hunt individual krill or small groups of them. This diversity of predatory strategies among different fish species illustrates multiple evolutionary adaptations converging independently to efficiently exploit the same fundamental food source, abundantly available in their shared environment. This compensatory reproductive capacity depends fundamentally on factors specific to this species' biology. Mature females produce multiple spawning events during the breeding season, each releasing thousands of eggs. An accelerated population growth rate, combined with a relative lack of significant predation during the early larval stages. When organisms are too small to interest most of the adult predators mentioned earlier, allows for population recovery fast enough to offset the massive losses suffered by adults during the subsequent intensive predation season. Food availability for juvenile and adult krill also directly influences reproductive capacity and subsequent survival rate. Phytoplankton blooms, occurring seasonally as sunlight and nutrients become available together, provide the energy needed for rapid growth and successful reproduction. This coupling between microscopic primary productivity and the reproductive capacity of a secondary consumer illustrates the complex interdependence that characterizes functioning marine ecosystems, where multiple trophic levels remain connected through constant, mutually dependent energy flows. The balance maintained between massive predation and compensatory reproduction, while seemingly stable based on historical observations, remains vulnerable to significant environmental disturbances. Ocean warming, changes in sea ice patterns, and shifts in phytoplankton availability could destabilize this carefully balanced equilibrium, with cascading consequences affecting all the predators that depend on this fundamental food source. The same extraordinary reproductive capacity that allows it to sustain an annual consumption rate exceeding half of the total population also reveals an inherent fragility. Any significant reduction in that compensatory capacity could trigger a collapse throughout the entire food web, a web built on a seemingly solid foundation, but one that actually depends on a precise balance between opposing forces locked in constant dynamic tension within that cold, remote ecosystem. Among the predators that depend on this prey species, the largest animal on the planet is also the one that consumes the most by daily volume. According to research from Stanford University's Hopkins Marine Station, a blue whale in the eastern North Pacific ingests, on average, 16 tons of krill in a single feeding day. During peak feeding, it lunges through krill schools 60 to 70 times a day, with each mouthful containing between 5,000 and 10,000 kilograms of water and krill combined, processing around 2,000 individual krill in a single mouthful. Until recently, it was estimated that baleen whales ate the equivalent of less than 5% of their body weight per day. It's now known that the amount consumed represents 5% to 30% of body mass, on average, 3 times more than previously thought. 16 tons is roughly the weight of 3 adult African elephants, devoured entirely in the form of tiny crustaceans during a single feeding period. That number, abstract at first glance, becomes concrete when compared to something tangible. Picture a truck fully loaded with small transparent shrimp, dumped entirely into a single animal's mouth, over and over, across just a few hours. No other known natural feeding process comes close to this scale, involving just one biological individual consuming prey that's individually so tiny in such a monumental quantity. The mechanics of this feeding involve an extraordinarily specialized body structure. The blue whale has a lower jaw capable of expanding dramatically, connected to the body through pleated elastic tissue called a ventral pouch, or throat grooves. As the animal accelerates rapidly through a dense concentration of krill, it opens its mouth wide, creating a temporary cavity that can hold a volume several times the whale's own body size. Water comes in along with the prey. Specialized muscles then contract that expanded cavity, forcing the water back out through filtering structures called baleen plates, while trapping the captured krill inside. Baleen plates, made of keratin, the same protein found in human nails and hair, replace conventional teeth in these whales. Hundreds of parallel plates, with frayed inner edges forming a structure like a fine sieve, line up along the upper jaw. Water passes easily through these microscopic gaps, while krill, slightly larger than the openings between the bristles, gets trapped efficiently. The whale's massive tongue then pushes the captured prey to the back, allowing it to swallow industrial quantities without any conventional chewing, a process completely different from what's seen in toothed predators. The speed of this feeding process is just as impressive as the volume processed. Each lunge through a dense school lasts only seconds, during which the whale accelerates rapidly, opens its mouth, captures a massive volume of water and prey, then slows down to process the captured contents before repeating the maneuver. 60 to 70 daily repetitions mean the animal carries out this complex cycle roughly every 15 to 20 minutes during active feeding periods, demanding precise muscular coordination and considerable energy expenditure, largely offset by the caloric efficiency gained through this mass capture strategy. The recent scientific review mentioned in this context represents a significant correction to previous understanding of these whales' energy needs. Earlier estimates, based on theoretical metabolism calculated through mathematical models applied to mammals of comparable size, considerably underestimated the actual consumption observed through modern tracking technology. Sensors temporarily attached to the animals, capable of recording movement, depth, and even acceleration during each feeding lunge, allowed for far more precise calculations of the volume actually processed during real feeding events, revealing consumption substantially higher than what had previously been assumed. The gap between the old estimate and the new understanding illustrates how advanced technology continuously refines scientific knowledge about animal behavior in natural environments that are difficult to observe directly. Previously, researchers relied mainly on indirect calculations, extrapolating theoretical caloric needs based on body size and estimated basal metabolic activity. Current methods, combining direct electronic tracking with sophisticated hydrodynamic modeling that calculates the volume of water displaced during each lunge, provide a far more accurate picture of these whales' actual behavior during intensive feeding seasons in the Antarctic Ocean and surrounding regions. The variation between 5 and 30% of body weight, depending on specific conditions, reflects behavioral flexibility adapted to the momentary availability of prey. When it comes across an extraordinarily dense concentration of krill, the blue whale maximizes its intake, processing amounts close to the upper end of that range. Under less favorable conditions, with more scattered concentrations, proportional consumption drops, reflecting the reduced efficiency of each individual lunge. This ability to adjust feeding behavior based on environmental availability shows considerable behavioral sophistication, allowing for energy optimization in an environment where resources vary considerably across space and time. The caloric need behind this massive consumption is directly tied to the extraordinary body size of these whales, which can exceed 30 meters in length and reach a mass of over 180 tons. Maintaining basic metabolic function, on top of the additional energy needed for constant swimming across vast oceans, and eventually reproductive migration between polar and tropical waters, demands a colossal caloric intake. Krill, despite being individually tiny, provides through mass capture enough energy density to sustain this gigantic metabolism when caught in appropriately massive volumes during concentrated feeding periods. Understanding the scale of this individual consumption sets the stage for looking at another predator with a completely different strategy, but equally dependent on this same fundamental prey species. A seal that, despite its name suggesting a crab-based diet, developed a specific anatomical adaptation aimed almost exclusively at catching the same tiny crustacean that also sustains the largest animal ever to exist on the planet. Among seals, one species took krill dependence to an evolutionary extreme. The crab-eater seal, despite its name, barely eats any crabs at all. Crab-eater seals developed special teeth as an adaptation for catching this abundant prey. Their unusual multi-lobed teeth let the species filter krill out of the water. They're the most abundant seal in the world. 98% of their diet is made up of Euphausia superba. These seals eat more than 63 million tons of krill a year. Leopard seals developed similar teeth, with krill making up 45% of their diet. The entire structure of these seals' mouths, teeth that interlock like a strainer, evolved specifically to process this single prey species in bulk. This species' common name causes considerable confusion among non-experts, suggesting a crab-centered diet when the biological reality points in a completely different direction. The origin of this misleading name traces back to limited historical observations or imprecise translations of the original scientific nomenclature, persisting through common usage even after later research revealed the seal's true dietary makeup. This mismatch between popular naming and observed biological reality shows how old scientific names, established before modern research methods existed, sometimes preserve factual inaccuracies that stick around culturally even after well-established scientific correction. Multilobed dentition represents a truly extraordinary anatomical adaptation, unlike any dental structure found in other marine carnivores. Each individual tooth, instead of having the simple conical shape typical of predators that catch larger individual prey, develops multiple cusps or lobes projecting outward to the sides. When the jaws close, these lobes from adjacent teeth interlock precisely, creating a complex three-dimensional structure that essentially functions as a biological sieve. Water passes through these interlaced gaps while krill, slightly larger than the resulting openings, stays trapped inside the mouth cavity, a process mechanically similar to the baleen system seen in the whales mentioned earlier. The feeding mechanism involves the seal swimming through a dense concentration of krill, opening its mouth to let in water and prey at the same time, then partially closing its jaws while expelling water through the specialized dental filtration system. Unlike predators that chew each captured prey individually, the crab-eater seal processes substantial volumes simultaneously through this continuous filtration mechanism, allowing efficient capture of numerous, but individually tiny organisms that wouldn't be worth catching and processing one by one through conventional hunting and chewing methods. This species' population abundance, often cited as the most numerous seal globally, is directly tied to the abundance of its main prey source. Population estimates vary considerably depending on the methodology used, but they consistently rank the crab-eater seal as the most numerous pinniped species on the planet, significantly outnumbering the combined populations of all other seal, sea lion, and walrus species worldwide. This extraordinary abundance directly shows how a massive supply of a specific food source can sustain a correspondingly vast predator population when specialized adaptation allows efficient exploitation of that abundance. 98% dietary specialization represents an extreme degree of dependence, rarely seen even among predators considered specialists in conventional biological literature. Most carnivores maintain significant dietary flexibility, switching between multiple prey sources as seasonal or geographic availability shifts. The crab-eater seal, by contrast, shows nearly absolute specialization, with just a tiny 2% fraction of its diet made up of occasional alternative prey, possibly fish or other small organisms caught incidentally during feeding events primarily aimed at capturing krill in substantial volumes. 63 million tons, consumed annually by this species alone, represents a substantial contribution to the total consumption mentioned earlier involving all predators combined. Considering that the total estimated range for seal consumption fell between 63 and 130 million tons, it becomes clear that the crab-eater seal alone could account for the lower end of that entire range, demonstrating the extraordinary scale of its individual impact on the krill population, despite being just one among multiple seal species inhabiting the Antarctic region. The leopard seal, mentioned for comparison, shows a notably different dietary pattern despite also having developed similar teeth adapted for filtering krill. A 45% dependence rate, while still substantial, leaves considerable room for other food sources, including penguins and smaller seals that this particularly aggressive species also actively hunts. This behavioral difference between related species, both possessing similar dental adaptations, shows how a shared anatomical structure doesn't necessarily dictate identical feeding behavior, with significant behavioral flexibility remaining even when the specific morphological capability is present. The evolution of this specialized dental structure likely happened through a gradual process across successive generations, with individuals possessing slightly more efficient dental variations for catching krill gaining a modest nutritional edge, which eventually translated into greater reproductive success. Repeating this selective process over an extended time span, combined with the target prey's consistent abundance, eventually resulted in the highly specialized dental structure observed today, a remarkable example of anatomical adaptation precisely tailored to efficiently exploit a specific food resource abundantly available in the shared environment. Understanding this extreme specialization in passive capture through specialized physical structure stands in sharp contrast to the behavior of the prey itself, which is far from remaining passively vulnerable in the face of so many specialized predators. Krill has developed its own sophisticated defensive and communicative strategies, including the surprising biological ability to produce its own light, a mechanism whose exact function remains only partly understood, but which certainly plays a significant role in this species' survival amid such intense and diverse predatory pressure. Despite being tiny, krill isn't a passive or inert prey species. It's often called the light shrimp because it emits light through bioluminescent organs located in different parts of its body. A pair on the eye stalk, another pair on the hips of the second and seventh thoracic segments, and individual organs on the 4 abdominal sternites. These light-producing organs periodically emit a yellowish-green glow, lasting up to 2 to 3 seconds, and are considered developed enough to be compared to a flashlight. The exact function of this light is still debated among researchers, but the most widely accepted hypothesis is communication within the swarm itself. A prey species capable of producing its own light amid the darkness of Antarctic waters, all while being hunted by dozens of different predators. Bioluminescence, the biological phenomenon behind this light-producing ability, results from a specific chemical reaction involving a substance called luciferin, which reacts with oxygen in the presence of a catalyzing enzyme called luciferase, releasing energy in the form of visible light rather than significant heat. This process, also seen in fireflies, jellyfish, and various other marine organisms, allows for the production of cold, highly energy-efficient light without the need for external light sources. Krill, spreading this capability across multiple specialized organs strategically positioned throughout its body, shows considerable biological sophistication for such a tiny organism. The precise anatomical distribution of these light-producing organs, described in detail by specific location, eye stalk, particular thoracic segments, abdominal sternites, suggests a carefully directed biological function rather than an accidental or vestigial trait. The eye stalk refers to the structure connecting the compound eyes to the main body. Placing a light organ in that specific spot could help with precise directional signaling. Thoracic and abdominal segments, distributed along the main body, could create a recognizable light pattern visible to other nearby individuals, which is especially relevant given the extreme population densities characteristic of these swarms. The specific color emitted, yellowish-green, isn't an arbitrary choice, but results from physical properties related to how different wavelengths penetrate seawater. Blue-green light penetrates more efficiently through the water column compared to other colors in the visible spectrum, making it consequently the predominant wavelength seen across various marine bioluminescent organisms, evolutionarily adapted to maximize the visibility of this light signaling in an environment where natural sunlight becomes progressively more limited as depth increases, eventually disappearing completely in the ocean's deeper regions. The limited duration of each light emission, specified as between 2 and 3 seconds, suggests active, voluntary control over this phenomenon, in contrast to the continuous passive bioluminescence seen in some other marine organisms. The ability to selectively turn light production on and off implies a nervous system developed enough to precisely control the timing and duration of this signaling, possibly in response to specific environmental or behavioral cues, allowing for temporally structured communication rather than simple constant, unmodulated luminosity. The flashlight comparison, mentioned as an illustrative reference, adequately captures the intensity and directionality of this biological light-producing ability. Unlike the weak, diffuse glow characteristic of some simple bioluminescent organisms, krill's system apparently produces light intense and directed enough to serve an effective communicative function, even in conditions of near-total darkness typical of the depths these animals frequently inhabit during the daily vertical migrations mentioned earlier, especially during daylight hours when they descend to avoid visual predators hunting near the surface. The communicative hypothesis, identified as the most widely accepted explanation currently, proposes that light signaling helps coordinate behavior within dense swarms. Given the extreme population densities mentioned earlier, up to 30,000 individuals per cubic meter, maintaining group cohesion and behavioral synchrony through purely mechanical or chemical mechanisms alone could face significant limitations. Light signaling, instantly perceived by nearby individuals, could complement other sensory mechanisms, facilitating the rapid coordination needed for synchronized evasive movements in the face of sudden predatory threats. Alternative hypotheses, while less widely accepted, also deserve consideration within the ongoing scientific debate. Some research suggests a possible function related to camouflage through a process called counterillumination, where the organism emits light through its ventral surface, offsetting the shadow that its body silhouette would otherwise cast against brighter light from above, making it less visible to predators looking up from below. Other hypotheses consider a possible role in attracting reproductive partners during mating periods, although evidence supporting this specific function remains less robust compared to that supporting the main communicative hypothesis. The apparent vulnerability of producing one's own light, precisely while being hunted by various predators capable of visually detecting that signal, presents an intriguing evolutionary paradox worth careful consideration. It's possible that the benefits gained through improved group coordination outweigh the individual risks tied to momentarily increased visibility, especially if signaling occurs preferentially in contexts where multiple nearby individuals already share similar exposure to potential predators. Fully understanding this apparent evolutionary contradiction remains an active area of ongoing scientific investigation. This light-based communicative ability represents just one facet among multiple behavioral strategies this prey species has developed to navigate the constant predatory pressure imposed by various organisms specialized in catching it. In addition, krill also employs a sophisticated temporal behavioral strategy, systematically moving through the water column in a predictable daily pattern, alternating exposure between different sets of predators as light availability shifts between day and night. Krill doesn't just sit around waiting to be eaten. It adopts a movement strategy that regulates its predators' access to it throughout the day. Most krill species carry out large daily vertical migrations, providing food for predators near the surface at night and in deeper waters during the day. Rising to the surface exposes krill to visual predators like penguins and seabirds, which hunt only when light is available. Descending during the day reduces that risk, but exposes the prey to another set of predators that hunt by echolocation in the depths. The result is a synchronized shift of hundreds of millions of tons of biomass every single day between two different predation regimes. Daily vertical migration, a behavioral phenomenon widely observed among planktonic organisms and small marine invertebrates, represents one of the largest synchronized biomass movements known in nature, occurring continuously across the world's oceans. In the specific case of Antarctic krill, this migration takes on truly impressive proportions given the total biomass involved, moving across hundreds of meters of depth twice daily, rising at dusk, descending at dawn, in a repetitive pattern maintained consistently across successive generations, governed primarily by natural light cycles alternating between day and night. The logic behind this behavior is directly tied to managing differentiated predatory risk between two distinct sets of predators, each relying on fundamentally different sensory mechanisms to locate prey. Visual predators, including various species of penguins and diving seabirds, rely fundamentally on available light to detect krill through direct sight. At night, with the absence or drastic reduction of sunlight, these predators' hunting efficiency drops considerably, creating a relatively safer time window for krill to approach surface waters where phytoplankton food concentration tends to be higher. Conversely, predators that rely on echolocation, including various species of toothed whales and possibly other organisms with similar sensory capabilities, don't depend on available light to locate prey, instead using the emission and reception of sound waves reflected off objects in the surrounding environment. These predators maintain relatively constant hunting efficiency regardless of available light, making greater depths, normally safer from visual predators during daylight hours, still potentially dangerous due to the presence of these acoustically oriented hunters, creating a complex behavioral trade-off that krill must constantly navigate. An additional energy benefit, often associated with these vertical migrations in various planktonic species, relates to differential metabolic efficiency between warmer surface waters and colder depths. Staying in colder waters during the day, when feeding activity is reduced due to higher predation risk, could lower overall metabolic rate, conserving energy that would otherwise be needed to sustain a faster metabolism at the higher temperatures characteristic of surface waters. This complementary mechanism could partly explain why this migration follows this specific temporal pattern observed consistently. Synchronizing this migration across vast populations, involving literally hundreds of millions of tons of biomass moving in coordination, requires some shared regulatory mechanism among individuals. While direct light detection through visual sensory organs likely represents the primary mechanism, allowing each individual to respond independently to changes in ambient light intensity as the sun rises or sets, the possibility of additional communication through bioluminescent signaling, mentioned earlier, could complement and reinforce behavioral synchronization within dense swarms, producing a more coordinated collective response than what could be achieved through isolated individual responses alone. The ecological consequences of this massive migration extend far beyond simple individual predator evasion, shaping the dynamics of the entire surrounding Antarctic ecosystem. Various predators have adjusted their own temporal behaviors to match krill's shifting availability at different depths over the daily cycle. Seabirds concentrate their hunting activity mainly during available daylight when krill approaches the surface. Predators capable of deep diving can exploit krill's presence at greater depths during daylight hours, creating a complex temporal pattern of differentiated predatory exploitation across a full 24-hour period. Vertical carbon transport, a significant ecological phenomenon tied to these migrations, occurs when krill feeds on phytoplankton in surface waters at night, then descends to greater depths during the day, eventually excreting carbon-rich fecal matter at those depths. This process, called the biological carbon pump, contributes significantly to atmospheric carbon sequestration on timescales relevant to global climate regulation, showing how a seemingly simple individual predator evasion behavior produces measurable biogeochemical consequences on a planetary scale, connecting the behavior of a single tiny organism to processes regulating the entire Earth's atmospheric composition. Variation in this migration occurs based on specific environmental conditions, including the presence of sea ice, phytoplankton availability at different depths, and even the direct presence of predators detected through various sensory mechanisms. During periods of extensive ice cover, the migratory pattern can shift, with krill potentially staying closer to the underside of the ice, where specialized algae grow, providing an alternative food source during periods when open water phytoplankton becomes less available due to limited light penetration through extensive ice cover. This massive daily movement, repeated continuously across countless generations of Antarctic krill, illustrates how a seemingly simple and vulnerable organism developed a sophisticated behavioral strategy to navigate an environment full of diverse predators, each specialized to exploit different conditions and specific moments. The synchronized movement of biomass equivalent to several times the weight of the entire combined human population, repeating daily between surface and depth, remains a fundamental ecological process sustaining the dynamic balance between this extraordinary prey species and the multiple specialized predators that depend on it for their own survival. In that remote, frozen Antarctic ecosystem where cycles of light, darkness, hunger, and flight keep repeating endlessly throughout the waters surrounding the frozen continent. Even the ocean's largest invertebrates, including the colossal squid, Mesonychoteuthis hamiltoni, capable of waging physical battles with sperm whales, indirectly depend on the same krill base that sustains seals and whales. Squid consume between 30 and 100 million tons of krill a year, the second largest share of recorded predatory consumption of this prey species, behind only seals. The entire Antarctic food chain converges on the same point of origin, from the 2-gram krill all the way up to the largest living invertebrate on the planet, passing through 150-ton whales along the way. The energy base is always the same microscopic prey multiplied by 379 million tons. The colossal squid, an organism whose very existence remained unknown to science for a considerable stretch of history, is one of the largest invertebrates ever documented, capable of reaching a total length of over 10 meters and a weight exceeding 500 kilograms. Unlike common squid familiar from cuisine or public aquariums, this species inhabits the extreme depths of the Antarctic Ocean, rarely observed directly, known mainly through specimens recovered by accident or characteristic marks left on predators that dared to confront it directly in underwater battles fought in the dark nearly inaccessible depths where it permanently resides. This squid's ability to physically confront sperm whales, massive predators specialized precisely in hunting deep-sea cephalopods through extended dives aided by sophisticated echolocation, demonstrates formidable physical defenses developed through evolution. Tentacles equipped with suckers fitted with rotating, hook-like structures allow it to inflict significant wounds when it actively resists capture. Characteristic circular scars, frequently documented on the skin of captured or observed sperm whales, provide valuable indirect evidence of these underwater confrontations, rarely witnessed directly by human observers. The indirect connection between this giant squid and the tiny krill operates through intermediate links in the food chain, rather than through direct predation between these two organisms so vastly different in size. The colossal squid feeds mainly on deep-sea fish and smaller squid. These, in turn, depend significantly on krill as a primary or secondary food source. Energy originally captured through photosynthesis carried out by phytoplankton, later concentrated through direct consumption by krill, gradually transfers through multiple successive trophic levels until it eventually sustains the metabolism of this giant predator residing in the most extreme depths of the Antarctic Ocean. The colossal squid's direct consumption of krill, specifically noted in that range of 30 to 100 million tons annually, suggests that a significant portion of its diet also involves direct predation on this crustacean, complementing the indirect consumption through intermediate prey mentioned earlier. The wide range in this estimate reflects the inherent methodological difficulty of studying the feeding behavior of an organism inhabiting extreme depths, rarely accessible through direct observation or even the conventional tracking technology efficiently applicable to other marine predators that are more easily monitored in relatively shallower waters. This squid's position as the second largest consumer among all the predators mentioned so far, outranked only by seals, is surprising given the relative scientific obscurity surrounding this organism compared to public familiarity with whales and penguins, charismatic species extensively documented through popular media and scientific research. The sheer magnitude of this consumption, placing it among the top krill consumers in the entire Antarctic ecosystem, demonstrates the substantial ecological importance played by this relatively mysterious species, whose basic biology remains only partially understood despite the impressive scale of its predatory impact on this fundamental prey species. The complete convergence of this food chain, explicitly connecting a 2-gram organism all the way to an invertebrate weighing hundreds of kilograms, passing through marine mammals of truly colossal proportions, illustrates a fundamental ecological principle broadly applicable across diverse ecosystems. Energy always flows from microscopic primary producers, capturing solar energy through photosynthesis, gradually moving up through successively larger and more complex consumers with each trophic level fundamentally depending on the one immediately below it to obtain the energy needed to sustain vital processes and eventual successful reproduction. The multiplication mentioned, microscopic krill multiplied by 379 million tons, elegantly captures the mathematical essence underlying this complete ecological convergence. An individual organism, weighing a fraction of a gram, becomes, through extraordinary population multiplication, an energy foundation sufficient to simultaneously sustain multiple predators of completely different sizes and strategies, from the massive passive filtration characteristic of whales to the specialized active hunting carried out by predators like the colossal squid in the most extreme depths of the surrounding Antarctic polar ocean. Understanding this complete convergence of the entire Antarctic food chain onto a single fundamental prey species inevitably raises the question of how vulnerable this ecological structure is to additional pressures, including growing human commercial exploitation, specifically targeting this same species, on which practically the entire Antarctic ecosystem fundamentally depends for the continued survival of countless species interconnected through this shared energy base. Despite the sheer volume of natural consumption, this prey species remains practically untouched by human fishing, even amid growing demand for krill oil and dietary supplements. In 2024, total krill catch reached just 500,000 tons, a mere 0.8% of the estimated biomass, and well below the precautionary catch limit of 5.61 million tons set by the Commission for the Conservation of Antarctic Marine Living Resources. Even so, in August 2025, for the first time in history, the industry hit the catch limit of 620,000 metric tons for the entire Area 48, forcing an immediate closure of the fishery. The most abundant prey species on the planet also remains the most carefully regulated, because practically the rest of Antarctic wildlife depends on it, directly or indirectly. The contrast between natural predatory consumption, exceeding half the total biomass annually, as mentioned earlier, and human commercial extraction, representing a fraction under 1% of that same biomass, illustrates a striking disparity between predatory pressure established over thousands of years through natural evolutionary processes and relatively recent human economic activity that's still comparatively limited in absolute scale. This substantial numerical difference suggests that, despite gradual growth observed in commercial demand, human fishing currently remains a relatively minor component within the full picture of total predatory pressure exerted on this species, which is fundamental to the entire Antarctic ecosystem. Krill oil, the main commercial product driving this fishing activity, contains a high concentration of omega-3 fatty acids, specifically the forms known as EPA and DHA, widely marketed as a nutritional supplement for human consumption. The extraction process involves capture through specialized nets, followed by relatively quick industrial processing, necessary due to the rapid decomposition characteristic of these crustaceans after capture, caused by digestive enzymes naturally present in their bodies that remain active even after death, rapidly degrading product quality if processing doesn't happen within a relatively narrow time window after initial capture. The Commission for the Conservation of Antarctic Marine Living Resources, the international organization responsible for regulating this specific fishing activity, sets precautionary limits based on extensive scientific modeling that takes into account multiple factors, including total estimated biomass, population reproduction rate, the food needs of dependent natural predators, and an additional safety margin protecting against the inherent uncertainties of biological estimates applied to vast, geographically dispersed populations. This multinational regulatory process, involving cooperation among various countries with fishing interests in the Antarctic region, represents a relatively unusual coordinated effort toward preventive management of a fishery resource before signs of overexploitation become evident through measurable population decline. The precautionary limit set, significantly higher than the actual observed catch, incorporates a substantial safety margin reflecting the conservative approach taken by regulators aware of the potential cascading consequences that excessive exploitation of this fundamental prey species could trigger throughout the entire Antarctic food chain. Unlike many global commercial fisheries where regulation often responds reactively only after signs of population decline have already become evident, management of the Antarctic krill fishery proactively seeks to set sufficiently conservative limits to prevent problems before they happen, recognizing this species' disproportionately significant ecological role compared to other conventional commercial fisheries. The sudden closure of the fishery, which happened in August 2025 when the specific limit for Area 48 was reached, demonstrates how this regulatory system works in practice when commercial activity effectively approaches previously established limits. Area 48, a specific geographic designation referring to a particular region within the Antarctic Ocean where most current commercial fishing activity is concentrated, has its own limit distinct from the total precautionary limit mentioned earlier, reflecting the uneven geographic distribution of both the krill population and the commercial fishing activity, specifically targeting it within this vast Antarctic region. This first-ever historical occurrence of a closure due to a limit being reached suggests a possible growing trend in the intensity of commercial fishing activity, even though it still represents a small fraction of the total biomass theoretically available. Rising demand for omega-3 supplements, combined with technological advances making capture and processing more commercially viable economically, could partly explain this unprecedented approach toward previously established regulatory limits, raising relevant questions about the future trajectory of this specific commercial activity as demand potentially keeps growing over the coming decades. The concentrated geographic distribution of fishing activity, rather than uniform spread across the species' entire range, creates the possibility of localized impacts even when total consumption remains proportionally small compared to the estimated global biomass. Concentration of fishing effort in specific areas, possibly overlapping with regions important for feeding natural predators, such as penguins breeding in nearby colonies, could create localized competition between human commercial exploitation and the nutritional needs of native wildlife, dependent on this same fundamental food source, even when the aggregate impact on a continental scale remains comparatively modest. The ongoing vigilance applied to this fishing activity, reflected through careful regulation and active monitoring of established limits, demonstrates scientific and regulatory recognition of this species' disproportionate ecological importance compared to the tiny individual size characteristic of each single organism. Unlike many other commercial fisheries where the target species occupies a relatively peripheral position within a broader food web, Antarctic krill sits at the center, making any significant disruption potentially cascading through multiple dependent trophic levels, which justifies the disproportionately careful regulatory attention it receives compared to other conventional commercial fishing activities around the world. The blue whale eats 16 tons of it a day. The crab-eater seal built an entire set of teeth just to filter it out of the water. The colossal squid, capable of leaving scars on sperm whales, depends on it at the base of the very food chain that sustains the squid itself. Penguins, seabirds, and entire schools of fish all revolve around the same daily vertical migration of hundreds of millions of tons. In terms of biomass, it's probably the most abundant animal species on the planet. A 6-centimeter animal, weighing less than a coin, glowing alone in the dark of Antarctic waters, and on which practically every marine predator in this ecosystem relies, to some degree. The ocean's most devoured prey is also the one that sustains practically everything that devours it. Revisiting this complete sequence of seemingly isolated facts reveals an underlying unifying pattern, connecting observations that initially appear scattered about predators so different in size, behavior, and feeding strategy. The blue whale, the largest known animal, and the colossal squid, residing in the most extreme and inaccessible depths, share an identical fundamental dependence on the same tiny organism, despite never directly interacting with each other within their respective, completely distinct ecological niches. This improbable convergence shows how complex ecosystems often organize themselves around relatively simple central points, capable of sustaining extraordinary diversity through well-established energy transfer mechanisms passed down through successive generations. The crab-eater seal's specialized dentition, mentioned repeatedly throughout this entire narrative, perfectly exemplifies how selective pressure exerted by the consistent abundance of a specific prey species can shape an entire anatomical structure through gradual evolutionary processes, extending across countless successive generations. A dental structure functioning as a biological sieve didn't arise randomly. It resulted directly from the reproductive advantage given to individuals capable of more efficiently exploiting this particularly abundant and predictable food source, consistently available across vast regions of the surrounding Antarctic Ocean. The light-based communicative ability, a biological mechanism allowing behavioral coordination within dense swarms, complements the daily vertical migration strategy, creating a dual system of behavioral adaptations that enables effective navigation through a complex, multifaceted predatory landscape. These mechanisms, operating simultaneously and possibly in a complementary, reinforcing way, illustrate considerable behavioral sophistication present even in an organism of extraordinarily small size, challenging simplistic assumptions about a necessary correlation between behavioral complexity and absolute body size across different animal species. The careful regulation seen in modern commercial fishing, contrasting sharply with the often more reactive approach applied to other global fisheries, reflects a matured scientific recognition of the central position this species occupies within the complete Antarctic ecological structure. Proactive regulatory vigilance, anticipating potential problems before clear signs of population decline become measurable, demonstrates the practical application of accumulated scientific understanding about the complex interconnections characterizing functioning marine ecosystems, where a significant disturbance at a central point could trigger cascading consequences across multiple simultaneously dependent trophic levels. Total biomass, comparable to or greater than that represented by the entire human species, places this organism among the most abundant currently known through extensive scientific research applied to diverse global marine ecosystems. The direct comparison between a centimeters-long crustacean and a species capable of building technologically advanced civilizations, both numerically converging in terms of total accumulated mass, offers a humbling perspective on the true scale of microscopic life multiplied across vast populations, often underestimated compared to the disproportionate attention received by individually larger and more charismatic organisms within conventional popular science narratives. This extraordinary reproductive capacity, allowing for consistent compensation of annual losses exceeding half the total population, represents perhaps the most fundamental biological trait sustaining the entire ecological structure examined throughout this complete sequence of interconnected observations. Without this robust compensatory capacity, none of the predatory relationships that subsequently developed, from massive filtration by whales to dental specialization in seals, to indirect consumption through giant squid, could have evolved or remained sustainable over time spans long enough to establish the deeply interconnected ecological relationships observed today. This inherent vulnerability, despite seemingly inexhaustible abundance, remains a relevant consideration in the face of potential environmental changes, including gradual ocean warming and shifts in sea ice patterns characteristic of the Antarctic region. The delicate balance maintaining reproductive capacity sufficient to offset massive predatory pressure, combined with the specific environmental conditions needed for successful reproduction, shows that even ecological structures that seem robust and have been established for thousands of years remain fundamentally dependent on relatively stable environmental conditions, potentially vulnerable to significant disruption should historically consistent climate patterns undergo substantial change. Over the coming decades, multiple predators, each developing a distinct strategy, mass filtration, dental specialization, active hunting in the depths, signaling, and the prey species' own behavioral migration, repeatedly converge on the same fundamental point of energetic origin. This repeated convergence, observed across completely distinct evolutionary lineages and radically different behavioral strategies, suggests that the abundance and predictability of this specific food source created, through independent evolutionary processes, selective pressure strong enough to repeatedly shape the behavior and anatomy of multiple species with no phylogenetic relationship to one another, all independently converging on the efficient exploitation of this same fundamental resource, abundantly available in the icy waters surrounding the Antarctic continent.